Hey, this is Presh Towalkar. In this video, I will present a collection of 6 interesting logical puzzles. Puzzle 1. A shape is shown in the following grid. The challenge is to cut the shape into 2 pieces and rearrange the 2 pieces so that you form a perfect 8 by 8 square. How can you solve it? The puzzle, as stated, is quite challenging. So let's cheat a little bit. Imagine the puzzle instead set to cut the shape into 3 different pieces. Would you be able to form a square? It would be pretty easy. All you have to do is cut off the squares that are sticking out. So make one cut here, make another cut here, and just rearrange these squares and put them into the missing squares. So all we need to do is place these squares over here, and we have created the 8 by 8 square that we want. But we have not solved the original puzzle. We have cut into 3 different pieces. So how can we solve the problem if we need to cut the shape into just 2 different pieces? Well, let's take that same idea of using these squares that are sticking out and try to put them into filling the gaps. So let's say we wanted this square to go into this gap. In order to do that, we would need to make a cut like the following. So we'll cut out here, we'll go across, and we'll cut out here. So now let's say we have cut the shape into 2 different pieces. So let's try to rearrange it. Let's rotate this cut shape. And now we're actually pretty close to the answer. We're only off by 1 square. We just would need this square to go into this corner. So instead, let's start over and let's go ahead and take one of the sticking out squares and put it into this gap. But now we need to make room for this other square that we rotate. So we need to cut out a square here. Now, if we cut out a square here, it's going to need to go somewhere else. So we'll make it go into this spot here. And this spot, we will need to put it somewhere else, and this will exactly fill the gap that we need. So let's see the cut that we need to make. We need to cut around these 2 squares. So let's go ahead and make one cut. Now we will cut around this 1 square. We will cut across, and we will cut around the other square. So finally, we make one cut, and now we have divided the shape into 2 pieces. So let's take this piece, and all we need to do is rotate it. And we will see that once we do that, we exactly will fill up the gaps, and we have solved the puzzle. Puzzle 2. There are 3 large and small circles placed alternatingly in a line. Your job is to sort the circles so that you either end up with 3 large circles and 3 small circles, or vice versa, where you have 3 small circles and then 3 large circles. But you are limited in the type of move you can make. The only legal move is to take a pair of adjacent coins and slide it somewhere else in the row. So here is one example of a legal move. Using only this type of move, how can you sort the circles? Let's work it out. So here's the beginning point. Here's one way you could solve the puzzle. Take these 2 circles and slide them to the right of the line. Now, take these left 2 circles and slide them right in the middle. Now I've run out of space, so let me just shift this entire slide over. This is not a move, I'm just making room on the right-hand side. And now we take this pair of adjacent coins and we slide it all the way to the right. And we have solved it. We have 3 small circles followed by 3 large circles. Puzzle 3. Scientists have successfully concluded an expedition to Mars and made contact with Martians. They uncover a scroll which shows extensive scientific and mathematical knowledge. They are able to decipher the scroll shows a mathematical equation, and it is also shown that this equation has 2 solutions of x is equal to 5 and x is equal to 8. So you try to understand what's going on. When you substitute x is equal to 5 into the equation, you do in fact get a solution. But when you substitute x is equal to 8, the value is equal to 45, which is not equal to 0. So this gets you to thinking. You have only substituted the values according to the base 10 system that we use on Earth. But obviously, the Martians are using some other number base for this algebraic equation. What number base are they using? Let's work through this problem step by step. Clearly, the coefficients of this quadratic equation are written in some other number base b. So let's first convert these coefficients into base 10. The coefficient on x squared is 5, and 5 in base b is exactly going to convert to 5 times b to the power of 0, which is equal to 5 in base 10. Now what about the coefficient of 50? When you write 50 in base b, that is equivalent to 5b to the power of 1 plus 0, and that will be equal to 5b in base 10. 125 will be equal to 1b squared plus 2b to the power of 1 plus 5b to the power of 0, and this simplifies to b squared plus 2b plus 5. So let's substitute these coefficients into the algebraic equation. So we will replace these and put it into base 10. So we have 5x squared minus 5bx plus b squared plus 2b plus 5 is equal to 0. Now what can we say about this equation? Well, the Martians have indicated that x is equal to 5 and x is equal to 8 are solutions. So we can substitute in one value. Let's substitute in x is equal to 5. We substitute and now we simplify, so we end up with a quadratic in b. This will simplify to the equation b squared minus 23b plus 130 is equal to 0. All that remains is to solve for b. So let's focus on this equation. We can easily factor it as b minus 10 times b minus 13, which gives us two solutions of b is equal to 10 and b is equal to 13. But we know that b cannot be equal to 10 because in that case, x is equal to 8 would be a solution, and we've already seen that x is equal to 8 is not a solution if we're working in base 10. So we can eliminate b is equal to 10, and it must be the case that Martians are working in b, the base is equal to 13. And that's the answer. Puzzle 4. Here's a fun geometry problem. We have a pinwheel shape made out of 4 right triangles. This distance is equal to 1, and this distance is equal to 5. What is the area of a single triangle? So how can you solve this problem? One way to approach it is to think algebraically. Suppose that the shorter leg of this right triangle has a length equal to x. That would correspond to this length right here. We now see that the length of the other leg will be equal to x plus 1. We are given that the hypotenuse is equal to 5. So we can now set up an equation. We must have x squared plus the square of x plus 1 is equal to 5 squared. We expand the binomial, collect like terms, and then divide by 2 and solve this quadratic equation. But wait, you don't need to solve the equation. We are trying to solve for the area of this right triangle. The area of this right triangle will be 1/2 the product of its legs. So it will be equal to 1/2 of x times x plus 1. So let's instead see if we can solve for x times x plus 1. Notice we have x squared plus x. So if we take a factor of x, we have x times x plus 1. Minus 12 is equal to 0. We then add 12 to both sides of the equation, and then we divide by 2 so that we get the area of the right triangle is equal to 6. And that's certainly one way you could solve the problem. But being a puzzle, there is an ingenious solution. we will solve this problem by rearranging areas. We will simply slide these triangles to form a new square. There's a square inside of the square which has a side length equal to 1. So how will this new shape help us solve the problem? Well, the area of this entire shape is that of a square with a side length equal to 5. But we can also calculate this area as the sum of the areas inside. The areas inside are 4 of these right triangles plus one square with a side length equal to 1. So the area of the square is equal to 5 squared. This is also equal to 4 times the area of a right triangle plus the area of a square with a side length of 1, which is 1 squared. This gives the equation 25 is equal to 4a plus 1, so that 4a is equal to 24, and a is equal to 6. The area is solved without resorting to quadratic equations, and it is just an ingenious geometric construction. By way of history, this is exactly the same argument that was used historically in order to prove a squared plus b squared is equal to c squared for the first time. It is known as the Gogu theorem in China. To give you an illustration of how this construction works, let's say we have a right triangle with a hypotenuse equal to c. One side is b and the other side is equal to a. So the square has a side length that's equal to c, and the small square inside will have a side length that's equal to a minus b. The area of this right triangle is of course 1/2 a times b. So we can set up our equation that the area of the square is equal to 4 of these areas of triangles plus this square in the middle. So we have c squared is equal to 4 times 1/2 ab plus the square of a minus b. We just expand this binomial and we see that 2ab from the area of the triangles cancels out with minus 2ab. So we get that c squared is equal to a squared plus b squared. And that completes the proof. Puzzle 5. You have a sack that contains 100 blue balls and 95 red balls. You are going to play a game. You draw 2 balls at random from the bag. If the 2 balls are the same color, you will throw those 2 balls away and replace them with a blue ball. So if, for example, you drew 2 red balls, you're going to throw those red balls away and you're going to put a blue ball into the bag. If you had 2 blue balls, you do the same thing. You throw those balls away and you put 1 blue ball back into the bag. What if the 2 balls are different colors? In that case, you're going to throw them away and replace them with a red ball. So if you had 1 of each color, you're going to throw those balls away and replace it with a red ball. You're going to repeat this process over and over until only 1 ball remains in the bag. The color of the final ball will be A, always blue, B, always red, or C, sometimes blue, sometimes red. So how can we solve this? Let's take a look at what each step would result in. So let's keep track of what happens to the number of blue balls and the number of red balls in the bag after each of these possible steps. So imagine we drew 2 red balls and replaced it with a blue ball. In that case, the sack would end up with 1 more blue ball than it started with, but it would be 2 fewer red balls. So that would be minus 2. If instead we replace 2 blue balls with 1 blue ball, well, the number of blue balls is going to go down by 1, and the number of red balls is going to be unchanged. Now, if we draw 2 balls that are different colors, we replace them with a red ball. So a blue ball and a red ball resulting in a red ball will decrease the number of blue balls by 1, and it will keep the number of red balls unchanged. So this is also true in the final case, where we have the number of blue balls is going to decrease by 1, and the number of red balls is going to be unchanged. So let's look at all 4 of these possibilities. We can notice a pattern in the change in the number of red balls. It's either going to be 0 or minus 2. Now, these are all even numbers. So the number of red balls is always going to change by an even number in each step. Originally, the bag had 95 red balls, which is an odd number. Now, if we take an odd number minus an even number, the resulting number will always be odd. So the number of red balls is always going to be an odd number. It is impossible to be equal to 0 because 0 would be an even number. In each draw, we are reducing the number of balls in the sack by 1. So after sufficiently many draws, there will only be 1 ball left. Now, 1 blue, 0 red is impossible because we can't have the number of red balls being an even number. So the final ball must be red. It must be that we have 0 blue balls and 1 red. Therefore, the final ball is going to always be red. The correct answer is B, always red. Puzzle 6. Here we have a shape formed by 7 equally spaced points, and we've connected every pair of points with a line. The puzzle is, how many triangles do you see? There's a systematic way to count the number of triangles. So what we will do is we will classify the different types of triangles present in this shape. One type of triangle will consist of each of the vertices of the triangle exactly being one of these 7 original vertices. Another type will have 2 of its vertices from the original 7, and the other vertex will be a crossing point of these edges. In other words, it's an intersection point of these diagonals of the shape. A third type of triangle will have only 1 vertex that is from the original 7, and the other 2 vertices will be these crossing points in the interior. A final type of triangle will have all 3 vertices being in these interior crossing points. So the next step will be to count the total number of triangles of each type. Let's start out with the first case, where all 3 of the triangle vertices are selected from vertices of the original shape. Suppose the original shape had n vertices. How many ways are there to pick 3 of these vertices? This will exactly be equal to n choose 3. So we have a correspondence between the vertices and selecting 3 of them to counting these type of triangles. Let us now continue to counting the next type of triangle. 2 of the vertices will be selected from the original shape, and the other vertex will be a crossing point of these diagonals. But notice we can associate this crossing point with vertices of the original shape. If we extend this line, it will reach a vertex, and if we extend this line, it will reach another vertex. So we could associate this triangle with 4 vertices of the original shape. So if we take 4 vertices, how many ways are there to select 4 from the original vertices? That's exactly equal to n choose 4. But now we need to make an adjustment to our count. Let's suppose that we connect all 4 of these vertices. How many different triangles can we associate with these 4 vertices? Clearly, it will be 4 different triangles where one of the edges is 2 of the original vertices. So here we have 1 green triangle originally shown. Here's another example. Here we have a third one, and here we have a 4th one. So there will be 4 triangles associated with each choice of n choose 4. So we need to multiply this by 4 to count all of these types of triangles. Let us now continue to the next type. Now this triangle has just 1 of the original vertices, and the other 2 points are crossing points. But let's associate those with vertices of the original shape. So we will take 1 point here, then we will extend this line to get to a vertex. We will extend this line to get to another vertex, and we have this line which will be associated with 2 vertices of the original shape. So we can associate this triangle with 5 points that are original vertices. So the number of ways that we could choose 5 of these points will exactly be equal to n choose 5. But how many triangles can we associate here? So let's connect all of these vertices. And we need to count how many triangles are there that have one of the original vertices and the other 2 points are crossing points. So it needs to be triangles of this type, and we can see in this shape there will exactly be 5 such triangles. So let's go to the original diagram. One triangle is illustrated. Here's another type. Here's a third one. Here's a fourth one. And here's a fifth one. All 5 of these triangles will be associated with these 5 vertices. So we need to multiply n choose 5 by 5 different triangles. So it's 5 times n choose 5. Finally, we have one more type of triangle where all 3 points are crossing points. We can associate this with vertices of the original shape. So every single edge will be associated with 2 vertices of the original shape. So we will be picking 6 vertices from the original set of vertices. So this will be n choose 6. And clearly, we will only be able to form one triangle because each of these edges will form one side of the triangle. So the number of these type of triangles will be n choose 6. So now let's put it all together. We have counted the number of triangles of each type. So in order to count the total number of triangles, all we need to do is add up each of these. And we have an incredible formula. N choose 3 plus 4 times n choose 4 plus 5 times n choose 5 plus n choose 6. In our problem, n was equal to 7. So we can substitute in and calculate, and this will exactly be equal to 287. Therefore, there are 287 triangles in this figure. Amazing! But the fun does not end here. Notice we have created a formula for a general value of n. So let's say we take n is equal to 9. How many triangles are in this shape? We can just substitute n is equal to 9 because exactly the same analysis will apply. There will only be 4 types of triangles. We have counted each of these types. So we substitute in n is equal to 9, and we can see that there will be 1,302 different triangles in this shape. This would be impossible to count by hand. You would surely lose track somewhere. But through this formula, we have just instantly figured out the number of triangles in this shape. But there is a caveat to this general formula. It will only apply where n is an odd number. So n is equal to 7, n is equal to 9, n is equal to 11, and so on. Now, why is it a problem when we have an even number? So let's take a look at a shape where we have n is equal to 6. If you were to apply this formula to n is equal to 6, the resulting value would be 111. But if you were to actually count the number of triangles in this shape, the actual value would be 110. You would be off by 1. Why are you off by 1? It's because of this point right here. So we have 3 lines that are crossing associated with 6 vertices, but we don't actually have a triangle here. We just have a point that is the intersection of all 3 of these edges. So this final value, 6 choose 6, is a false triangle. We actually need to deduct this value of 1. So instead of 111, we have 110 triangles. So when you have an even number, you end up that some of these triangles are false triangles. You just have these 3 edges that coincide at one point. So you need to adjust for this in the count. To illustrate the point with another example, let's take a look where n is equal to 8. If you were to just apply the formula and calculate, you would get a result of 644 triangles. But in this particular shape, there are only 632 triangles. Once again, we have a set of 3 different diagonals that are meeting at a point instead of forming a triangle. So we would need to adjust for the count of this final 4th type of triangle. That's the only triangle that we are overcounting, and in this case you would need to subtract 12 to get to 632. So this got me wondering, is there a general formula where n is an even number? So the good news is that there is a formula. There is an article called The Number of Triangles Formed by Intersecting Diagonals of a Regular Polygon. The bad news is that it's a fairly complicated formula. It's not that easy just to write out. But for those interested, feel free. I've shared a link to this paper in the video description, and you can probably work through it and figure out a closed formula, and you'd be able to calculate the number of triangles formed by intersecting diagonals of a regular polygon, whether n is even or odd. So let me summarize the results. In this video, I've shown how you can count the number of triangles for n points that are joined in a general position on a circle. It's exactly the following formula: n choose 3 plus 4 times n choose 4 plus 5 times n choose 5 plus n choose 6. By general position, I mean the points are not equally spaced like a regular n-gon. You would shift the points slightly so that you wouldn't have any intersection of 3 different diagonals of this polygon. So it won't be a regular polygon, but you would get a total number of triangles for n points joined in a general position on a circle. This formula is always going to be true. And when n is odd, it will always work. But you will have false triangles when n is an even number. It's relatively going to be small compared to the total number of triangles, but if you wanted an accurate count, you would need to take into account these false triangles. So you would take these total triangles and subtract the false triangles to get the formula for the triangles for a regular n-gon with all diagonals drawn. As illustrated earlier, when n was equal to 6, there was exactly 1 false triangle. So from the total 111, we subtract 1 to get to the true count of 110 triangles. When n was equal to 8, we saw those intersection points, and that created 12 false triangles. So we'd go from 644 minus 12 to equal 632. And actually the total number of false triangles is a small percentage compared to the total number of triangles, but if you needed an accurate count, you would definitely want to account for these false triangles. I think it's truly amazing that there is just a formula to calculate this out. What an amazing puzzle. Thanks for making us one of the best communities on YouTube. See you next episode of Mind Your Decisions, where we solve the world's problems, one video at a time.